Okay, we are going to graph y equals e to the x. Is the number e new to you?
Yes and no.
Yes and no? Do you know what it is approximately? Pi is 3.14.
It's 10. It's a number like 10.
It's 2 point something, you're right. E is approximately 2.7, and it keeps on going. But it seems to be easier to memorize than pi because it looks like there's a pattern. Even though you go 1828, 1828, you don't keep doing that. After that, it goes crazy just like pi does. But it is a number, and we use it a lot when we learn about exponentials and logarithms. So we're going to have to graph it. Now, graphing it is exactly the same as graphing 2 to the x or 3 to the x. You set up your grid. Every single exponential graph goes through 0, 1. This one, when you plug in 1 for x, you get 1, e, or 1, 2.7-ish. It increases just like every other exponential graph, and it has an asymptote at y equals 0. So that's the graph of y equals e to the x. And so if you had another one to graph, so y equals 3 e to the x minus 2 plus 1. We could do our transformations in the same way we did our transformations with our other graphs. You would have to recognize the parent graph has a base of e, an exponent of x, and we already graphed that above. So what do? We take the 2 points, 0, 1 and 1, e, and our asymptote, and do all the transformations that we had. So going from left to right, all of our stretches and compressions. That 3 would affect the y's. You'd multiply your y values by 3. We have no horizontal stretches or compressions in this one. So starting off, we would just multiply our y values by 3. Now what am I going to do with 1, e? How am I going to write that? 1, 3e. So that would keep it as an exact value. If you had a calculator, you could change that to 3 times 2.7 and write down whatever that is, but we'll try to keep exact values as much as we can. And then we do our translations. The minus 2 would be 2 to the right and up 1. So in the end, we're going to get 2, 4 and 3, and how are we going to do that with the 3e? Well, it won't be 4e because that would be 3e plus e. It'll just be 3e plus 1 because they're not like terms. This is the best that you could do. And our asymptote, the only thing that's going to change your asymptote at y equals 0 is if you move things up or down. And we moved it up 1, so we'll have y equals 1. So then when we go to do our final graph, you can start with your asymptote at y equals 1. Plot your points. 2, 4 and 3, 3e plus 1. So now this is where you might want your calculator just as an estimate, or maybe you can do 2.7 times 3 and say that's 8.1 plus 1 will be about 9.1. So I'm just going to estimate where that point is. Once you have those 2 points, you're going to be able to tell, well, this has to go up like this, and there's our graph with an e involved. So it's not necessarily harder, it's just more awkward because you're not dealing with nice numbers. Just like when you work with fractions, you could run into more mistakes just because it's not a number that you're used to working with. But the ideas are exactly the same. So you graph your parent function first. You've got your y equals e to the x. Recognize that in your new graph, and then do your transformations with your 2 points from there. What would be your y-intercept? How do you find a y-intercept? Put in 0 for x. So if I put in 0 for x, there's my y-intercept. That would be what it would look like. Of course, you could plug that into your calculator and get a decimal. It should be a little bit higher than 1 because of how our graph is. But the ideas stay the same. Even though the numbers that we're working with are not numbers that we're used to, the ideas stay the same. And so not only now can you graph anything, any exponential with any base, because you could graph the parent function and then do your transformations, you could also graph exponentials with the base of e.